that work okay for the mic? Sounds okay? I'll try and remember to talk into it. Perfect. So my name's Dale. Today I'm an engineering manager at Vendasta. I've held a number of individual contributor roles before that, and I've broken a lot of things through my career. So first off, show of hands, who here has made a release, deployed something, changed something, and had to deal with the resulting critical incident that follows up? Well, good, about half the crowd. The other guys, you need to ship more frequently. Okay, so this talk is a little bit about that time I fucked up, and they happen. Part of it is incident management lessons and some of the stories that come along. And hopefully you learn a little bit about infrastructure, some of its failure modes, and the types of failures that I've introduced over the time here. If you see my diagrams and you see where the story is heading and you see the failure, please hesitate to yell out, "You're an idiot." I know I'm an idiot. I was past an idiot. Today, if I look back, I will be an idiot. That's fine. So let's kick this off with some stories and some infrastructure. So first, I want to talk about the time that I orphaned the majority of our Kubernetes cluster. So one of the operations that we do frequently is Kubernetes updates. You take the underlying nodes, you replace them, you upgrade their version, all while keeping all your microservices running and whatnot. My mental model of how a network works is something like this. You've got a number of Kubernetes nodes that are running a specific version. You've got microservices that are scheduled over top of those loads. And then you've got load balancers that sit in front of those microservices. And traffic comes in the load balancer, hits the microservice, all things are magic. So my operation was actually to change the running version of the Kubernetes nodes, which isn't usually a big deal. You take the existing node, you create a new node pool that's on the new version, you cordon the old node pool, and then you tell Kubernetes to do a drain, which it basically kicks every pod off while respecting its pod availability budget and reschedules it on the new node pool. And according to my mental model, the load balancer hits the microservice, which hits the new version. Let's talk a second about scale. So I work at Vendasta. We're a software as a service company. At the time of this incident, we had about 70 microservices running. They're all kind of Golang microservices. They run in a shared Kubernetes cluster. We had 3 environments at the time: a test environment, a demo environment, and a production environment. And every microservice we host has both a gRPC load balancer and an HTTP load balancer. And those we're using Google Cloud load balancers that are managed service. They give us a load balancer. We don't have to really think about it. You basically provide a front end with a port and back end where it points to. So pretty simple setup here. But if we think about scale, 70 services times 3 environments times 2 load balancers, we had about 420 of those running within our cluster. And if we dig into one of these load balancers, you can see here that it's got at the top a TCP port, and then at the back it is a collection of VMs, which doesn't exactly match that diagram that I showed before, where load balancer points to microservice, points to node. Load balancer actually points to a collection of VMs that are running the Kubernetes instances. So that's where my mental model of how a network works is broken, and the resulting failure is a result of that thought. I was thinking that we were pointing our load balancers to the microservices where they're actually pointed to the nodes. We relocated our microservices, and the happy path of the routing is that the load balancers point to the old nodes, which then routes the traffic to the new nodes that then routes the traffic to the microservices. Failure mode comes from the fact I moved all of the nodes to the new version, and then went ahead and hit the delete button and removed all of those old nodes because I didn't need them anymore, because obviously we were serving off all of the new nodes, which orphaned around 400 load balancers. They no longer were able to route traffic to their microservices because they couldn't find the node pools that they were routed to. So this is the first case where I fucked up. So what happens next? When you break something, what is that moment and what should you do? Well, first off, you should tell someone. You're kind of in this alone until the point that you pull other people into it. And even if it's entirely your fault and you didn't mean to do something and there's a horrible outcome, tell somebody. Turn to the person next to you, let them know, I just broke stuff. And that helps work through that incident a little bit smoother. The second piece is assigning roles. In an incident, there's a number of common roles that are defined there. And there's a lot of writing on different roles in incidents and how to handle incident. But generally, it's things like the incident manager that is accountable for the entire process. You may have a tech lead that's accountable for actually fixing that particular area, who's an expert in the specific domain. You probably have somebody taking care of communications, working with your support group, letting them know you need to publish some type of a downtime alert, talking to customers. You may have somebody on the customer support side. You may have a subject matter expert in a particular domain. You may have somebody that's a scribe that's actually going to take notes of what is being changed in the running environment, or what are you updating, or what's being adjusted. The important thing to remember here is that you own every role until you delegate them. As the person that broke that particular piece, it's on you until you say to somebody, hey, can you reach out to support and let them know this is busted? Hey, I'm going to need somebody that has more experience in the storage layer than me. Hey, can you talk to the sales team? Go knock on doors, open up meetings, do the things that you need to coordinate those pieces. Hey, keep notes on what we change in our running environment so that we can roll it back or fix it afterwards. So basically, you assume every role until you ask for help. So the important piece there is asking for help. Second is pulling in critical resources. It can be super intimidating to file a P1 ticket with Google, or reach out to an external vendor, or go talk to the CTO about that thing that you just broke and the entire platform's down. But pulling in those critical resources and doing that early will keep you from getting burned by not doing it. And it's easier to cancel a ticket and go, whoops, my bad, than it is to actually get that thing escalated at the time when you're after the fact. So definitely pulling the critical resources, and if anything, the success of an incident is generally around communications and how well you communicate. So it doesn't necessarily matter that you patched it in a few seconds or worked through this. It matters that you communicated successfully and the right people knew and were able to manage that message and share that communication. So going back to this incident, I deleted the old Kubernetes version where all the load balancers were pointed at. It turns out Google load balancers take between 3 and 5 minutes to move when they detect a network change in here. That's a serial operation, so 400 load balancers can take a day plus to actually move as they go through here. We hadn't noticed this in previous versions because we had some stateful services running in the same Kubernetes cluster, things like RabbitMQ that had their own queue pieces and took a really long time to balance themselves. So in previous node upgrades, it would take 3 or 4 days in order to complete that operation successfully, and the load balancers would just automatically move behind the scenes so we wouldn't notice. But in this case, we were really quick, and we had offloaded those things to their own cluster and optimized for that case, and just let me delete it. So we had to sit there and manually reconfigure about 400 load balancers to point to a node pool that actually exists, and then it would bring those services back online serially as we made those changes. So we had 4 or 5 of us. We started at the bottom of the list, at the top of the list, in the middle of the list, and just kept going until we got all of the services moved. And because they're really nice, unique names in there and not named as services, it was challenging to figure out which ones were critical or more important, so we just kind of did them all in bulk. But ideally, you would figure out which services are most important and restore those first. The next major lesson from breaking things is afterwards decompress. In this instance, we all went over to Congress and had a beer, spent a little bit of time socializing and understanding that, yeah, these things happen, supporting each other, and taking a break away from it. When you break something, there's a whole bunch of stress that gets piled in immediately. There's emotions that are involved. Taking a little bit of time to decompress and step away from the incident makes a major difference in how you approach work in general and feel about walking away from that. So, if somebody breaks something, you want to make them feel better, go out for lunch with them, take a step away from work, it will help them handle those pieces. Okay, so next incident. Another time that I fucked up here. Let's talk about how I put our Elasticsearch cluster into a split brain scenario. Okay, so the basic structure of our Elastic cluster. We run a Kubernetes cluster. We have Elastic data nodes basically mapped 1-to-1 over top of those Kubernetes nodes that exist. Then each one of those Elastic data nodes has a series of indexes that exist on it. From a screenshot, the nodes look a little bit like this. So we have ES data node 1, it has 66 shards of data on it, node 10, 67. Basically, Elastic balances itself out over a large number of nodes, and then it manages a collection of indexes within that. So each one of these is an index for a specific purpose that has in our software. We have replicas, either a primary or a secondary replica, and an index may have 1 primary and 3 replicas or whatever's configured on top of that. So Elastic basically manages the balancing of those particular pieces and allocation of them to give you a performant database that can be queryable. So we were having a problem where we were seeing underlying node restarts within this cluster. All of a sudden, we would see a node go offline, and then that's not usually a huge deal. It can happen during a maintenance operation, and a node would go offline, and Elastic would have to rebalance itself to deal with this node no longer being there. Then, a couple hours later, another node would go offline randomly, and Elastic would rebalance. And it started to get to the point where it's getting a little concerning, where we're seeing more of these than normal. If Google's providing some type of a major operation, you may see this roll through really slowly, or you may see the occasional VM or node restart. But seeing a handful of them throughout a day in a cluster that is highly available and generally doesn't see that is a problem. So, as you do in a situation, we opened a Google ticket and was like, seeing these node restarts, here's the logs, here's the details. Google support responded back with something along the lines of, your Kubernetes cluster is about 2 years out of date. You should probably update that before you file a support ticket, and we're not supporting that right now. So this is where I fucked up. I decided to update Kubernetes, which in doing an update, you take nodes offline in order to update them to the new version. So it looks something like this, where we had a large number of nodes, and many of them were offline at the same time. A combination of just random node restarts plus the maintenance operation that I was taking on in order to upgrade it to the most recent versions so that I could get Google support to actually look into why those nodes were restarting. In hindsight, I probably should have pushed harder on support to actually look into the existing problem before I mess with it a little bit, but we ended up in this state where a percentage of the nodes were offline. Unfortunately, there's also this little line in the Elasticsearch docs. It says, by default, Elasticsearch will create indices simply by pushing data into a non-existing index. It'll create it in all the mappings we get for that data. So when we started to have nodes go offline, there was no longer a primary for some of these indexes, or the primary and the secondary was offline. In that case, when we tried to write our data from our existing microservices, it just created brand new indexes for us. And now we end up in a state they call a split write, which is where we have two data sets. We have the data set that came as a creation of those requests that were coming in that didn't have an index to write into, so it created brand new indexes. And we had the orphaned indexes that were around forever and were very large but not recoverable then. So we ended up in a state where some percentage of our Elasticsearch cluster and a number of the indexes were just no longer available and completely gone. So how do we go about fixing this? Cody's probably going to cringe here because I took an ugly screenshot when he wrote something. But we have a tool called vConstable, which we basically would go over every data store entity. And luckily, Elasticsearch is not our primary data store. We use Cloud Data Store or Cloud Span. But we would go over data store and we basically put or touch every single entity within data store, and that would just sync through the post-put hooks, everything back to Elasticsearch. So my next major lucky piece for this piece is prioritize the important bits. So not every index is actually treated the same way. There are pieces that are really important, like the list of accounts that exist within our system. And then there's things like email content or stats about executive reports, or just things that are not regularly in there. So really trying to take an index of what is the broken data, especially in a state where it's going to take a long time to restore, and then prioritize the really important bits to put that stuff back. Kind of the side effect here is also that it helps in an incident to get lucky. So the reason that we knew really easily how to reindex all our Elasticsearch data is because we left the Elasticsearch cluster unsecured at one point, and it was the victim of a cryptojacking attack where they had just left a ransom note saying, pay 3 Bitcoin to this address. And we had to rebuild one of our non-production environments as a result of that. So we had scripts already ready to go that said, this is how you rebuild Elasticsearch from touching data store through that. In this case, we did work with our Google team pretty closely. They were not happy with the response that Google gave me about update the cluster first. We were having some troubles with them, and they ended up covering the cost of this reindex operation, which was about $15,000 in data store rights in order to re-put all those entities and cause all the syncs that went off there. So it did help to still have a ticket filed. Upgrading the latest version didn't exactly fix this, but they found an internal issue and re-put it through there. So it does help to get lucky in an incident. That's one that I've come back to a few times in here. Can't really control it, but it's 100% helpful in recovery. Okay, so the next time I fucked up. This one isn't directly me, but I sat next to the person that was as involved as anybody else in it. So in this case, we deleted a number of core microservices in our platform, including things like our accounts, our identity and access management, our storage layer, and our account group layer. So at Vendasta, we tended to keep pet Kubernetes clusters. And they always say, treat your clusters as cattle and, don't give them names, give them numbers, and, make sure that they turn over very quickly, and that'll give you a healthy system. That's very much not the case we're in. A lot of our clusters were created upfront manually and had run for multiple years from pre-1.0 Kubernetes versions up until the 1.2s, 1.3s. There's a number of things that came out as features in that time that we weren't able to take advantage of, like multi-masters, where we were able to have multiple replicas of the master for Kubernetes, so that when you did something like an API update, you didn't lose access to the kube control command pieces. They didn't have multi-region clusters originally, which was something that we wanted to take advantage of. So we had some motivation to migrate all of our running microservices from one cluster to a new cluster that would then be in this case, regional, and have multi-masters and a bunch of those benefits. So that wasn't really that difficult. You've got a cluster, you've got the namespaces that run on top of that cluster, which are like logical groupings. We've got our deployments that run within the namespace, and then the deployments mount secrets and keys and all the things that they need at runtime that you don't really want checked into GitHub. So we were running this migration, and it kind of went like, I have a new cluster, I have an old cluster, and I basically want to take the namespace, and I want to create a namespace, I want to migrate the secrets, I want to migrate the deployment, I want to check health. Then I'm going to switch the DNS entries from the old cluster to the new cluster, then I'm going to delete the old namespace. Pretty straightforward. We had 120 services probably at this time, and had run this for probably 110 of them successfully. So we have the majority of our cluster running in this new piece. The only things that weren't running were a handful of bespoke services that were kind of stood up manually or super early in our cycle, and were different from the rest that were checked in. So as part of this walkthrough, we create the namespace, migrate the secrets, migrate the deployment. We got into that handful of the hard ones, the last ones that we were going through, but we're picking those off kind of as a team working together on how we were to stand those up and make sure they happen. So we got one of them moved and we worked through this set. We got to the very last step of it, delete the old namespace. It's like 8:30 in the morning, and there's definitely not enough coffee on board at this point. And I don't want to throw him under the bus, but Braden types kubectl delete namespace, which Kubernetes comes back with. It says you have to specify a namespace, or alternatively say -- all, which is a pretty standard response to it. You need a namespace or a namespace. So he types kubectl delete namespace -- all. Of course, he wanted to delete everything in that namespace. We're just removing it. Which then kicks off the deletion of all of the namespaces and everything that kind of passed through. So we deleted the last set of really hard services to move that are core to our cluster. So this is a space where we got really lucky. We had attempted to move some of these core services before between the clusters. So what we were left with was basically a namespace, no deployments running in it, but all of the associated files that went through it, like the secrets. And the really core piece here is the service we deleted was our identity and access management service. And identity and access management needs secrets that are a number of keys that are signing every request. So if we deleted that set of secrets, we would have had to roll every SDK to every customer, to every service, regenerating all of those keys across our platform. It really highlighted that we don't have a very good backup of our secrets that exist there. We got very lucky in this case that we had attempted to migrate this before and left those artifacts around and got through there. So this was a case where we got very lucky, but we were able to, in about 30 minutes, stand back up those services that were core to our platform and restore the service to the customers that we had broken. A couple lessons from there. If you have the opportunity, keep configuration code, even if it's simple configuration. It's really easy to open the cloud console and say, I want a new database, and I want it to be this size, and have this type of SSL certificate on it, and hit create. The problem is defaults change over time. Configuration is not always consistent. The options that go through there change. So if you don't keep that configuration in code, it makes it really hard to do diff or stand that piece back up, or have the same piece that you were running previously through the console. And here 4 or 5 years later, you have no idea what the person selected the first time when they went through that. So keeping configuration in code is a big step towards making sure that your configuration actually goes through the same code review, it's versioned as things go through. If you get an opportunity, this will save so many hassles, even on simple configurations, to check them in and follow that process. It would have been way, way easier for us to run a kubectl apply-f and just put a file back in and stand back on our service, but that didn't exist because we didn't have to check. The other major piece we learned from this is minimizing the startup dependencies. What we found when we got into the core services that were left in that cluster was things like our identity access management is a startup dependency of our storage system, and it's a startup dependency of our accounts system. Our storage system is a dependency of our accounts and our identity access management, and accounts is used by everything into our system. So we had this like circular dependency between the three services. And we had to constantly go through the code and comment out the startup pieces that were referencing those pieces, get something running so that we could start the next service and make that work. So you get an opportunity to look at your startup dependencies. It's almost always a space to optimize and to try to minimize as many of those possible. Because if you lose a critical service, it's really hard to stand everything back up again when you have all those things across. Okay, through another one. Let's look at another time that we found it. So this is probably the largest and most impactful outage that the Nest has had in the 11, 12 years that I've worked there. So we were having a normal week. Again, I did a Kubernetes update, moved all the nodes from one version to another version, all our services were running. And at this point, we had Envoy instead of 400 Google Cloud load balancers in front of it. You tell me that 400 Cloud load balancers was bad architecture. We recognize that. We changed that. Now we're running Envoy in front of them instead. So we had this kind of mental model that Envoy, it's a microservice, runs on top of nodes. I did the Kubernetes update on Tuesday. About 3 o'clock Friday, we poured beers and got paged that the entire platform was off. Like, latencies were through the roof, nothing was responding. Our reaction was restart Envoy. Like most things, restart the load balancer, everything works again. So did that, things were fast, went home for the weekend. Got to about 9:30 Friday night, get paged again, massive latency across all our applications, log in remotely, restart Envoy, everything's happy again. Okay, we get some type of a load balancer problem with the system. Restarting it fixes it, things are good. So we continued this delete all the Envoy pods and restart it every half hour to 15 minutes for the rest of the weekend. The more frequently we deleted Envoy, the more frequently it failed, and things got super slow again. So a couple of engineers joined in, and we spent the majority of the weekend pounding our head trying to reduce load from cloud services, our event broker system, our storage system, trying to give more resources to systems. What is being bounded here? Why are we suddenly seeing seconds of latency injected across all of our services and across everything? Is Envoy getting bad routes? Is gRPC versions having problems? Are we having streaming issues in there? So we ended up getting to Sunday, bringing in the critical people. We've got the CEO, we've got the CTO, we've got our VP of engineering, we've got everybody is aware of what's going on, and we're going into Monday going, this is going to be a shit week. We put together a war room with everybody in the same space, managing communications outwards. We had Google engineers dialed in. We're telling Google, we did this update on Tuesday last week. It worked fine for 3 days. We're sniffing gRPC connection problems. We're digging in deep into what's going on here. Google just keeps telling us we don't see other people seeing this. We're not having the same challenges. You guys seem to be the only ones that are screaming about this. Something's going wrong here. So one of the lessons we learned here is you do need to sleep. If you think an incident's going to run a long period of time, figure out what the handover looks like. Who are you going to hand it off to? What boundaries are you going to set for time? Because you can probably only put in 4 to 6 hours in an incident before you're like, I'm burned, I'm not thinking clearly, I'm going to do something stupid in the system. So you need to sleep. That's a key lesson. Make sure you have somebody to hand off to and formalize that handoff as you work through the incident. So, as we're responding to this incident, I think as Dustin brings up, we did a Kubernetes update, we should roll that back. So we create a new node pool on one previous version of Kubernetes. We migrate the vast majority of our microservices from one node pool to another, leaving a couple behind because we still want a sample group that we can see if this is failing, what is actually happening. So we left our demo environment, our identity access management, and we moved all the other services over to the previous Kubernetes version, all sitting behind Envoy, and the world was good again. There was no errors, no problems, things were fast. In fact, one of the comments from some of our executive team was, when it works, it's the fastest it's ever been. It's like, that's kind of weird. Let me write that in my notebook and we'll come back to it later. The next morning we come in and the entire platform is down again, massive latency, and the previous version of Kubernetes that we were running with most of our services is gone. When I set up that, again, not from config, but from the UI of saying like I want to provision a previous pool on the previous version, I left auto updates on. So overnight, it auto-updated the Kubernetes version and it migrated all of our services back over to the new version, and everything was busted again. So obviously, we just found exactly where the problem was. We didn't. So we go back to this configuration that we ran our identity access management, we left the previous version on, we shut off auto-updates, and we went about our lives. We continued to work with Google. Every couple of weeks, we bring it up in our calls. Does anybody else log this? Have you seen anything from our gRPC logs? Like, what could possibly be causing this latency? It's about 4 or 5 months later, we do some cleanup. We delete the latest version of Kubernetes. Kind of talked about, like, do we just skip a version, skip a major version, work through something like that. So we've done some cleanup and we were running the previous Kubernetes version, all of our services on it, all through Envoy. Well, here we go again. Everything starts crashing. This time it was at 4 or 5 hour increments when we would delete everything, and it was continually getting faster. We delete everything, we were basically DDoSing ourselves as all those things retried and broke those connections and went through it, and we'd see a wave of traffic that took a little while to get through. We were failing. So with some extensive digging at the time, we ended up finding a DNS log that says this. The maximum number of concurrent DNS queries was reached, maximum 150. So we start digging in and really trying to draw the diagram of what's happening here. Well, in the docs, this is kind of how kubedns works. Your pods call to a kubedns server, and it, within your cluster, has kubedns pods that have all of your DNS pieces, and if it has to, it goes outside to Cloud DNS. Well, kubedns has this configuration running in it. And at the time, our clusters were running 16 replicas of 16 core machines. So we were basically running 2 DNS pods for a 256 core cluster, all running Golang microservices, which are pretty efficient and can make a pile of requests in them across the setup. So we were sitting right at the peak in both the number of nodes per replica with 16 and the number of cores per replica with 256. So what was happening was when we created a new node pool to roll back to the previous version, we were actually bumping the number of replicas in our cluster enough that it would add a different DNS pod, and it would have enough capacity to handle all of our traffic. And when we would delete that particular piece, we would get back down to 16 and 16, and we didn't have enough DNS capacity within this cluster. So I think one of the big lessons here is it's always fucking DNS every single time. Just if something's in doubt, it's DNS. One of the takeaways I took from that is to write future queries. So when the executive team was saying, when it's working, it's the fastest it's ever been, that was a trigger that we should figure out why it's faster than it's ever been before. And through any incident, writing down the different things that you've been asked, that you've known, or that you want to learn about coming through there can be really good post-mortem topics, but they can also be future things that help you improve the system that you wouldn't otherwise take if it wasn't for the case of having a particular incident. So in this case, if I'm working in your system, this probably looks like that. I'm probably going to break something at some point, and it's going to be horrible. But digging into the future queries here, we found out that it was actually CFS wait time that was causing our applications to be slow. So if you put a limit on a container in a Kubernetes cluster, it's going to make sure that it stays within that amount of compute. It actually takes the amount of compute that you've allocated and windows it over microseconds, and will force you to wait till the next window in order to continue processing that request. And there's certain systems in our application stack that would always run not at limit, but closer to limit. Things like our Envoy proxy and our identity access management and some of our storage pieces were resource heavy, and we wanted to constrain those to a certain point, and we put limits on those. But if you're approaching your limit in a system that uses CFS to schedule compute resources, it'll introduce latency to every one of those requests until it has enough window to be able to handle that piece. So we'd actually see, tenths of a second in latency in some cases for an access management check that would be just single milliseconds otherwise. So by setting a higher threshold on the limits and removing that capacity piece and really adding monitoring across our entire platform for CFS wait times, we're able to vastly improve the performance of the platform without actually changing the compute or changing any of the logical code that goes through that. So CFS wait time is an important piece, and that comes out of actually writing the future queries that do that. So my highlights from this: if you break something, make sure you tell someone. Make sure you assign the roles that you're not doing absolutely everything. Make sure you get a little bit lucky. It definitely helps. Sleep when you can. Draw the diagram to make sure that you fully understand the system and you've considered all of the different layers of the stack, especially if you just can't seem to find that next step in troubleshooting. And write down the future queries that you get from it. It'll help you when you get to the point of having a postmortem or finding your next steps within the app. So this is my contact information. I'm sure we can share it out afterwards if we need to. If you've got any questions, if this is interesting to you, or you want to talk further about breaking things or how to run incidents within your organization, I'd be more than willing